Hi everyone. Today I would like to talk about Bayesian versus frequentist estimation. So Bayesian versus frequentist in general is very hot and controversial topic in statistics. Today I only focus on the Bayesian versus frequentist estimation. I try to explain what they are and which one is more appropriate for your application. Now let's start with the frequentist approach. So the Bayesian versus frequentist, they have some subtle differences on how they define actually some concepts. One of these concepts is probability. Frequentists define probability as a relative frequency of an event in a long run. So for example, what do I mean by that? Let's say you want to calculate the probability of head in a fair coin. According to the frequentist point of view, you toss a coin 1,000 times, and then you count the number of times that you have had divided by 1,000. You will have a proportion or relative frequency. You repeat this 1 million times, 100 million times in the long run for n very large. That's how they define the probability. But as far as the estimation is concerned, um, frequentist approach, they assume the parameter theta, the parameter we are trying to estimate, is fixed and unknown, right? So they would construct something known as a likelihood function, and they will maximize this likelihood function with respect to the parameter to find the optimal value of this parameter. So how do they construct this likelihood function, and what is this likelihood function anyway? So the likelihood is the probability of observing the data of the data given the parameter. So mathematically is denoted by this LF, and this for likelihood. Theta semicolon x is probability of x given theta, probability of data given the parameter. So one another subtle difference between the frequentist and Bayesian is that frequentists only use the data to construct the likelihood. They don't use any prior knowledge or whatsoever they have about the problem. They only use the data and they assume the parameter is fixed and unknown. So, and also they construct a likelihood function. We talk about that in detail in a minute. Now, on the other hand, Bayesian approach, they define the probability as a measure of uncertainty or belief about an event. So, for example, going back to the case of a fair coin, if you want to calculate the probability of a head using Bayesian approach, you say that I don't have any reason to prefer the head over the tail. So my uncertainty or my belief about head and tail are equal. So both of them will have probability 0.1. In terms of the estimation, they will assume the parameter theta to be a random variable. It's not fixed anymore. Bayesian school of thought assumed theta to be a random variable with an unknown distribution. So what do I mean when it's a random variable? When it's a random variable, it has a distribution. It has CDF, cumulative distribution function. It has PDF if it is this continuous. If it has PMF, if it is discrete. It has mean. It has a standard deviation. It has second moment, third moment, fourth moment, and so on and so forth. Right? Very good. Now, Bayesian, they use data, but they will add also prior belief for estimation. So instead of using the likelihood function that we discussed in the case of frequentist, they use posterior distribution. So they use the likelihood and the prior belief to construct the posterior distribution. And during the estimation process, they will try to maximize the posterior distribution to find the optimal estimator. Now, let's see what I mean by that. So posterior distribution for a parameter theta is defined as P of theta given x. Means that the belief that I have about the parameter theta after I observe the data, x is data. Okay? Now, in order to understand this better, we need to talk about one of the most fundamental and one of the most crucial concepts in the whole probability statistic machine learning, which is called Bayes' law. So Bayes' law is an algorithm or is a method to relate the posterior and the likelihood distribution together, or to relate two conditional probabilities together. It can be used in general in any mathematical equation or any mathematical modeling. Okay, so let's say the parameter theta is the parameter that you want to estimate, right? In a Bayesian approach, you have some prior belief about the parameter. Before you even observe the data, before even you collect the data, you have some prior belief about your parameter. This prior belief is considered as this P of theta in the right-hand side of equation 1. Now, then you will go ahead and observe data. You will go ahead and collect the data. And you construct a likelihood function, this P of x given theta. This is a likelihood function. You will multiply them together. And of course, since posterior is a probability, you need to normalize them. You normalize the P of x, which is the probability of data. This equation 1 is known as the Bayes' law. The term in the left-hand side is known as the posterior distribution of theta. Means the probability or the belief that I have about the parameter after I observe the data. This P of theta is a belief I have before I observe the data, and the likelihood is what I construct, or is the probability of observing the data given the parameter. This P of x is probability of data or probability of evidence. Okay. So I wrote it down here that the P of theta is prior belief about the parameter, and P of theta given x is a posterior belief about the parameter after you observe the data. Now that we know what is the Bayesian and what is frequentist, frequentist try to maximize the likelihood, Bayesian try to maximize the posterior. Now we need to know what's the pros and cons of using each. How do I know that which one is better for my application? Now, Bayesian approach is computationally more expensive than frequentist. Why this is the case? You write the Bayes' law, P of theta given x posterior, you let the numerator to be prior times the likelihood, but look at the denominator. It might be innocent looking expression, but it's not really that innocent. This P of x can be written as P of x and theta integrated over whole theta. This is the concept of marginalization, right? And then according to the definition of a joint and conditional probability, I can write P of x and theta to be equal to P of x given theta times P of theta. Hence the equation 2. Okay? Now, I have to integrate respect to theta. This theta can be n-dimensional parameter. So you're integrating in an n-dimensional space. This integral can be really hard to calculate or sometimes impossible, right? Therefore, estimating this integral is a computationally expensive process, which makes the Bayesian approach much more complex than a frequentist approach. In terms of estimation, we will talk later on in other videos about MAP and ML. When you want to estimate the theta that maximize the MAP, you don't need to actually calculate the denominator because the denominator is independent of theta. The P of x has no theta in it. But in general, in the Bayesian approach, we are talking about the intuition here. The Bayesian approach is more complex and more computationally expensive than the frequentist approach. So I wrote it here, thanks to the denominator of Bayes' law, refer to equation 2. The Bayesian method is more computationally expensive than frequentist approach. But now, depending, there is another difference between the frequentist and Bayesian. Look at this equation 2. Or look at the equation, the Bayes' law, the original Bayesian equation, equation 1. There is in the numerator this time. In the frequentist approach, we have only P of x given theta, the likelihood function, this one, right? But now in the Bayesian approach, we are going to go ahead and add the prior belief. Is this a good thing or bad thing? It can be both. If we don't know anything about our problem, and we go ahead and choose a prior belief naively for our case, then when we multiply the likelihood and the prior, we get some sort of posterior after we normalize that. This might not be a good indication, or it's not, it could be a good representation for our problem. maximizing this might not give us any reliable estimator. This is called uh, the choosing informative or useful prior for our problem. Now, if you can choose a useful or informative prior for your problem, in that case, you can incorporate your domain knowledge or you can incorporate your expertise into the problem, which is one of the advantages of the Bayesian approach or the frequentist, right? So I wrote it down here that depending on how you choose a probability of the parameter, prior belief, the Bayesian can have advantage or disadvantage over the frequentist. We have some sort of informative or useful prior, then the posterior will be a better representation than a prior than likelihood, because you have more information, you have more useful information you incorporate into your problem. But if you have an incorrect prior and wrong prior, then the posterior will not be as good as the likelihood. Then the frequentist is better than um, Bayesian. One of the example here is, for example, a digital communication system. We always usually in real world assume that the probability of 0 and 1 are equal. So we pretty much, instead of using the Bayesian approach, we use a frequentist and maximum likelihood, which I'm gonna later on explain about that in the next video. But if you believe that 1, for whatever reason, in your case, happens more likely than 0, then using the Bayesian approach or using the MAP, maximum posterior probability, that will be discussed later on, you can go ahead and incorporate this prior belief into your problem. In the next video, I'm going to talk about the MAP versus ML. I'm going to tell you how to formulate the problem using MAP and ML, and how to optimize your problem, or how to optimize, calculate, or compute the parameter theta that maximize the MAP or ML problem. By the way, I have written also at the same time with this video, I've written an article in the internet which has all this equation, all this information here. These videos are all only explanation to help you understand that article better. I try to give a link in the description of this video, below this video, to that article. You can click on that article, read the entire estimation process. I'm gonna design the videos according to that article to make sure that it's easier for people to follow. Please, if you like this video, please subscribe to my channel, like the video, share the video with anyone you like, and see you guys in the next video. Thank you.